Hello everyone. Free radical part 4. This is continuation video of the previous one, that is part 3, where I have started the stability of free radicals. So in that video we have seen that both electron withdrawing group as well as electron donating group can stabilize free radicals because their behavior is not like conventional electrophiles. So I will suggest you to watch that video first so that you can understand this video in a better way. Okay. So here we have taken molecular orbital diagram to understand how radicals can be stabilized by electron withdrawing group. So when there is electron withdrawing group present, for example we have C double bond O or C triple bond N. So we have low lying pi star orbital in these groups. So as a result, here this is the radical in the left hand side, as you can see, containing this single electron, that is I am talking about before the MO formation. And in the right hand side we have this low lying pi star orbital which may be present in these types of electron withdrawing groups. Now once the MO is formed, there is only one electron present. The new SOMO that is formed, this is the previous SOMO, old SOMO, singly occupied molecular orbital, but after MO formation, the new SOMO which is of lower energy, and this electron now it will be here. So here you can see energy of the radical drops because electron is in a lower energy orbital compared to the situation when MO is not yet formed. So in this way, electron withdrawing group can stabilize the free radical. What about the other case, that is when electron donating groups are present? How then stabilization is occurring, we will see now. When there is electron donating group, suppose we have groups like OR, that is ether. Now here we have non-bonding electrons. So N orbital containing this lone pair which is basically present in the electron donating group like this RO group. Okay. Now before the MO formation we have one electron which is the electron of the radical, and we have these two electrons as if the lone pair present over this heteroatom oxygen. Now once the MO is already formed, we have total 3 electrons. Here we have 2 electrons that are coming from the donating group. Here we have only 1 electron. So total 3 electrons. So out of these 3 electrons, 2 electrons now they are placed in newly formed lower energy orbital. Okay. Now 1 electron is still there which will be here present. Now as this is single electron, so we are calling it high energy SOMO or singly occupied molecular orbital. Now if you are thinking that this single radical now compared to the previous situation where MO is not yet formed, compared to that situation now it is having higher energy, right? Then how it is stabilized? So you have to remember the fact that overall stabilization we have to consider. Though it is true that the single electron now it is in higher energy SOMO compared to the old SOMO, but 2 electrons now compared to the previous situation now it is in stabilized condition. Only 1 electron it is in higher energy SOMO. So though the only electron it is in higher energy, but remember that overall stabilization is there, we are getting in the overall system. Okay. So though the new SOMO it is of higher energy than the old one, we have to consider the overall stabilization of the system. So 2 electrons now it is in lower energy, only 1 electron is in higher energy. So considering this overall effect, we can say that radicals can be stabilized by electron donating groups. So we have seen now both electron donating group and withdrawing group in the MO diagram, how it is stabilizing the radicals. Next we have to see some examples of persistent free radicals. So there are some radicals that are more persistent and we call them, that is that we use a term persistent free radicals because they are more stable compared to other radicals. Now what is the reason of their stability? It may be electronic stabilization. Electronic stabilization you have already seen, that is both electron withdrawing group, donating group, and remember it is also including conjugation, then hyperconjugation, inductive effect. So these 3 terms that I have just said, that is inductive effect, conjugation and hyperconjugation. In carbocation reactive intermediate, the way they stabilize the carbocation, in a similar way they also stabilize the free radicals. So all these terms they come under electronic stabilization. But sometimes steric hindrance can also make these radicals more persistent. And the third possibility, both. So it may be that it is stabilized only by electronic factors, that is electron donating group or withdrawing group, conjugation, inductive effect, hyperconjugation, or it may be for steric reason, that it is so sterically hindered it cannot react with some other substance or it cannot dimerize, and sometimes it may be for both. So look at these examples. Okay, one more point. They have long lifetime because they are resistant to dimerization. So because of steric factors, they cannot come close to each other. So this is the reason they are resistant to dimerization, also disproportionation, and the other ways by which they can destroy themselves. That is the other routes of self-destruction. So see, these are the examples. So here if you consider the first one, here we have, this is the radical, here we have donating groups. So electronic stabilization is there. Then if you consider these 4 methyl groups, there is steric hindrance also. Come to the next one. Here this radical, it is stabilized by this donating group which is present just beside it. Then we have 3 benzene rings, so conjugation is possible. We also have electron withdrawing groups. So you can see here electronic stabilization, conjugation, steric hindrance, all these things are present. So you can say that both the factors, electronic as well as steric, both are playing some role to make them more stable. And then one more example, here also we have benzene ring, so conjugation is possible, which will give stability to this free radical. And there we have 3 tertiary butyl group which is making it sterically hindered. So that is why the other routes of cell destruction, that cannot take place easily. Okay, so that is why these are the examples of persistent radicals. Now some historic information. The first radical ever to be described in organic chemistry is triphenyl methyl radical. It is also known as trityl radical. So here we are synthesizing it from this PH3 CCl, okay, triphenyl methyl chloride, and with the help of this radical. And as you can see here, this carbon chlorine bond is broken and chlorine is shifted to Ag, and we are getting this triphenyl methyl radical. Now this triphenyl methyl radical, there is conjugation possible, and also because of steric reason, because here in this picture if you are thinking that all these 3 benzene rings they are in the same plane, actually that is not the case. They remain in this twisted form. Okay, so dimerization will be difficult because 2 such radicals, they cannot come close to each other. Now dimerization like this, that is keeping this structure constant, that is PH3C dot, another PH3C dot, this type of dimerization is not possible. But remember, another way dimerization is possible, which is like this, and it is known as Gomberg's dimer. So this is actually not happening. We are getting this one, and this dimer we can also see the extended version of the same structure. Here we have this PH3C, so this is PH3C part, then we have this ring, and then CC double bond and 2 more phenyl ring. So same structure, just it is drawn in a different way. So this triphenyl methyl radical, or you can call it trityl radical, undergoes dimerization, but not this type of traditional dimerization. It is a different type of dimerization in presence of copper or silver to produce this this dimer, which is having this name according to a scientist name, and it is a yellow colored solid which is soluble in organic solvent, and it is also stable at room temperature. Okay, so to summarize what we can say, the following factors will stabilize a radical. So electron withdrawing group, electron donating group, how they are stabilizing, that we have seen in today's video in the molecular orbital diagram picture. Then you can consider hyperconjugation or any conjugating groups. Now these hyperconjugation conjugating groups, the same way they stabilize carbocations, and if you are having any doubt regarding that, how hyperconjugation, conjugation, that is conjugating groups are stabilizing carbocation, please watch the videos of carbocation, and the playlist link you will get right now, the upper right corner. Okay, so there you will find how these factors are stabilizing carbocation. So same way they can also stabilize radicals. So all these are basically electronic factors. But remember, steric hindrance also can stabilize free radicals. Okay. So that's all about stability of free radicals. I'll meet you in the next video with some probably reactions of free radicals. Okay. Thank you for watching.